There is something you need to know, because if you get this wrong, it could cost you an absolute fortune. And your hobby will be ruined. So let's get stuck in. Today we're talking about speakers and amplifiers killing speakers. Oh, it's gruesome. Did you know that a speaker is a motor? This is probably what you think of as a motor, but this is a motor as well. This is a solenoid, and this is a speaker. And yes, they're all motors because look, you've got coils and magnets, coil and magnets, movement in that direction backwards and forwards, coils, magnets, movement backwards and forwards. So they're all the same. They are all motors. And that's the point. They all work in the same way, so they've all got the same sort of problems. And that's where we're going to start. So let's start with this simple solenoid. It's just a coil of wire and a metal rod. When you send current through the coil, it makes a magnetic field, and that field pulls the rod in. Boom, that's a motor, a straight line motor. Now look at the speaker inside. There's a tiny coil glued to the cone that sits in a magnetic gap. When music flows through the coil, the magnet pushes and pulls it, and the cone moves air. That's a motor too. It's one that vibrates instead of spinning. And here's your classic electric motor. Same idea, coils, magnets, currents, but this time the magnetic push makes the motor spin. Solenoid, speaker, motor, same trick, different motion. Now we're getting on to some of the nitty-gritty and the gruesome stuff. Now let's talk heat. Pass a big electric current through a coil of wire and you get heat, like we used to in the old days with electric heaters. This is a rule of physics, but what we want is sound power, not heat power. This is the effect we want, but we don't happen to have the divine intervention, so we've got to do it with good old-fashioned engineering and physics. For our purposes, there are two types of electricity. There's AC, which you get from power stations, and DC, which you get from batteries. But actually, it's not quite that simple, but we'll go on with it. Ooh. DC is there. It's just there. AC comes and goes. Well, actually, it goes positive, and then it goes negative. And in between it's zero. Basically, because the AC isn't the same value all the way through, you have to work out what its effect is. So where it's over 100 volts, it gives more push, and where it's under 100 volts, it gives less push. What that works out at is that you get the equivalent of 100 volts from 141 volts, and that's what we need to know. But remember, it goes in both directions, which gets life even more complicated. So a 4.2 watt amplifier is putting out about 5 volts DC. 20 watt amplifier is putting out 11 volts DC. 37.5 watts equals 15 volts. But the trouble is, although the speaker might be rated for 100 watts audio, these DC numbers are brutal because DC equals continuous heating. No airflow cooling. The coil stays still, no movement, and you end up with big problems. The glue former and coil insulation will all heat up steadily. Even 10 to 20 watts of DC can cook a coil over time. Time is the killer, as well as the DC. Where does all this DC come from? Well, the simplest answer is this one. Look, you've got 35 volt rail. That means the supply of 35 volts goes through one component, which is the transistor, the driver transistor, which can go short circuit, and then you go into the speaker, and the speaker goes to earth. So that's 145 watts of power going through that speaker just because the transistor's gone short. The output transistor going short circuit is relatively rare, and on most good quality amplifiers there's actually protection to try and prevent your speaker being damaged, but there's no guarantee it's going to work, and there's no guarantee you got it. It depends how much you pay for your amplifier. Now the other one, this one is more, the source of DC is more sort of subtle, and you're going to have to bear with me a bit on this one, so here we go. Do you remember this? We said it pushes all one direction hard, or the AC goes up hard and then back down the other direction. But no, it's not always the same. Well, this is where it gets interesting. This is an AC square wave, and you can see here it's either fully on in one direction or fully on in the other direction. There is no in-between time. It's not like a sine wave where it's got time off. This is extortionate working. No time off. It's very difficult to get waves that mean anything, but sound is not very often very neat. That's what it looks like. But this is what a real sound is. This is two trumpets. You heard them earlier on. This is what it's like in the middle, and again in the middle, and then at the end. Now the thing is, those waveforms are real. And they don't mean an awful lot when you look at them, but look at this, 45 dB, 33 dB, 28 dB. What that means is, in actual fact, the ambient power, the power where it's just sitting there running, is 17 dB difference. And that equals 50 times more power being used on the big numbers than on the small numbers. While we're at it, you've heard about tweeter damage. Look, this is the maximum power, this is the fairly high power. And look, see, there's a difference. There's a whole spike there that wasn't there before. And what's more, that spike is at minus 6 dB, which means that it's actually at a very high power level. Now, if you've got a tweeter that's suddenly got that going up it, no wonder its eyes are water. So now you get it. The end result is quite important. Look, the power difference is 10 dB. And 10 dB means 10 times more power, which is an awful lot of power. So it means that you're going from, if you were going from 10 watts, you've gone to 100 watts. Look here, it says final result, 10 dB. Practical meaning for your PA is a 10 dB drop. A 10 dB drop in power is a tenfold reduction. So if a minus 6 dB corresponds to, say, 100 watts, the minus 16 dB corresponds to 10 watts. And now we've got the final answer, 17 dB. That's the difference between the different powers in a real world meaning for amps. If an amp is delivering 100 watts at one level, 17 dB would demand about 5,000 watts, even if the amp can't actually deliver it. That would be, even a small dB change can push an amp from clean to catastrophic. Well, so there you have it. That's quite important. You don't have to worry too much, but it just means you've got to be careful. If you've got a £5,000 speaker, you're doing it going, fuck. That's with a PH, by the way. And yeah, if you've got any other problems with speakers, you've got to be careful. I mean, if you stick plugs in at loud levels, you'll get transient damage. You can actually pop this cone, and the whole thing goes very wrong very quickly in that respect. Anyway, if you've got any experience with speakers, maybe like to put it in the comments. If you found any use, maybe like to pass it around, make sure anybody else who's got anything, because I don't think most people understand the magnitude of the problem. The fact that it can take such a little bit of difference to make such a huge difference to the end result. Anyway, that's it. Catch you another time. Like, subscribe, and see you again. Bye bye.